Good morning, good afternoon, good evening, everyone, and welcome to today's EMEA webinar on hydrogen infrastructure. My name is Mattia Cazzanica. I'm the executive sponsor of this initiative and of the working group paper which is associated to today's webinar. I will have a quick introduction of what we are going to have today, and I will hand it over to all the presenters which are covering all the topics today. Basically, we are having this webinar as hydrogen infrastructure has become a very central topic for engineering and construction insurance over the last few months. And we are anticipating the work which have been done for the working group paper on hydrogen, which will be fully presented at our EMEA conference in September this year. Anyway, we will be in a position to have the webinar today and at the same time to publish an EMEA Insight document, which will provide a very detailed overview on the technical and insurance features of hydrogen infrastructures. So that's the aim of today's webinar, and it will last for around 45 minutes, followed by a Q&A session. To encourage more lively discussion, we are proposing you to ask any questions during the presentation in the chat. At the end of the presentation, you can also raise your hand and ask a question when the administrator will allow you to speak. In case a question will not get answered during the webinar, we will try to follow up via email in due course. As you have seen, a recording of the webinar has been started and it will be available with the presentation and the EMEA Insight paper on the EMEA website in the next few days or immediately after this webinar. As I said, basically today we will not have an automatic distribution of attendance certificates for CPD and IDD purposes, but in case any of the attendees would need to have one, please email Stephanie Jocelyn at emea.com, so then we will be in the position to send you the certificate for the attendance. I already took too much time. We have an amazing panel of presenters for today from insurance industry, from hydrogen industry, and from the academic world, which I want to hand over the presentation. So we have Isabella, Isidro, Louis, Jan Sebastian, Franco, and Carla speaking and presenting. They will briefly introduce themselves, and it's my pleasure to hand it over to Carla Dilla for the first part of the webinar today. Please, Carla, go on. Thank you.
Thank you very much, Mattia. Thanks for the warm introduction. Hi, everybody. Very warm welcome from my side. My name is Carl Dill of Swiss Re Corporate Solutions, and I will be taking you through the agenda for today. Next slide, please. So here we can see the agenda. It's roughly going to follow the same structure than we have used in our paper. So we will be talking about the background of hydrogen in the first place and why it is relevant, then mention some of the technical aspects such as hydrogen production, industrial applications, transport and storage, and then talk about risk in the sections on underwriting, coverage and claims. Next slide, please. Now, when we start with the background on hydrogen, why is it relevant to talk about hydrogen now? It is because the hydrogen industry is very young and it's in a sort of dilemma, and that has a lot of implications on risk management. So this is why we thought we as EMEA should bring the topic up now. When we talk about dilemma, what does this imply? What does this mean for us? On the one hand, there are plenty of green lights concerning the hydrogen industry. There's unprecedented political momentum. COP26 has reconfirmed that the Paris Agreement cannot be met without the use of hydrogen. Pretty much every G20 nation has its own national hydrogen strategy. We, in fact, list 20 of these strategies in our paper, so it's worth taking a read. There's a strong pipeline of projects. The IEA has an online database with more than 300 projects already that have been developed, and further 400 projects are in early stages of development. So this is really growing fastly. There's a very positive outlook when it comes to the cost of hydrogen, which is also driven by the low cost of renewable electricity and economies of scale but also the CO2 price will likely render gray hydrogen less competitive, and this is going to reduce the cost of green hydrogen. Now, and lastly, there are new industry players coming as the traditional industry boundaries blur in the hydrogen economy, mainly from the oil and gas world. So there's plenty new expertise and plenty new capital. Now, on the other side, there are unfortunately many roadblocks, and these need to be considered carefully. Firstly, the hydrogen industry is not growing fast enough to meet the Paris targets, says the IEA, and there's much more political support needed. In fact, also investment. There's almost a false sense of complacency. If you read some of the studies on hydrogen, such as, for instance, the DNV report, the Energy Transition Outlook, it will say that the industry is only going to scale in the 2030s. Now, that raises the question for people why they should engage now. And there's a simple answer to this, because the hydrogen economy, the rules of this economy, the standards, they're being defined right now. So it's worth to take a seat at the table. A lot of hydrogen projects are highly integrated and have complex value chains. Think of joint ventures such as renewable electricity producers, hydrogen producers, and hydrogen off-takers. What are the risks in these joint ventures? And more importantly, who is managing these risks? And lastly, and this is a very important point, there's a lack of standards and best practices in the industry. The standards that we have right now are not focusing on project certification as in its entirety. And this is why organizations like DNV and the TÜV have launched joint industry projects to actually engage with industry stakeholders to achieve more and better standards. Now, for us as IMEA, the question really was, how can we secure insurability and bankability in this vital industry? Our mission, of course, as IMEA is to make a meaningful contribution when it comes to risk management. And we want to engage a community beyond just insurance professionals. We want to reach out to risk managers, to investors, in fact, to anyone dealing with risk in this vital industry. And there's one last thing I would like to say, and that's probably true for all of the reports that you've read about hydrogen so far. They have been published prior to the geopolitical tensions that we are seeing at the moment. And we are waking up to a new energy world, one that is clearly focused on renewable energy and on energy independence, excuse me. And it is clear that hydrogen is going to play a key role in this world. So with this said, I would like to hand over to my colleague, Isabel, for the first technical part. Thank you very much, Isabel.
Thank you, Carl. So my name is Isabel Escobar from HDI Global, and I want to show you the hydrogen production methods. The first slide.
Excuse me, Isidro, can you please put it in presentation mode?
It is already. You can see the presentation?
Yes, it's okay. It's fine as it is. We can also, it looks like I can see 2 slides, but it's fine. It will work. If you can't change it now, don't worry.
Okay.
That's better.
Okay, thank you very much. So, well, as Carl mentioned, hydrogen is a very promising and powerful energy carrier. It's not found freely in the nature, and therefore it must be obtained or produced from other compounds. The conventional way to produce hydrogen are fossil fuels. The hydrogen production from fossil fuels accounts for about 96% of the total hydrogen production worldwide, which is about 90 megatons today. However, in order to reduce the CO2 footprint, there is more focus on producing hydrogen from renewables. So the main development that we are seeing right now is the hydrogen production from electrolysis. Isidro, could you please put the electrolysis? Okay. So what we see is that nowadays about 4% of the hydrogen production is done from electrolysis, but we expect that in the next years about 8 megaton of the hydrogen is going to be produced from electrolysis. There is a very interesting graph from the International Renewable Energy Agency that shows that up to the year 2050, the hydrogen production will be increased from renewables from 4%, what we have right now, up to 22%. You can see the graph right now. What is very interesting also in this graph is that the hydrogen production from coal will increase from 18% to 33%. This is due to geopolitical effects and also due to costs. Next slide, please. So what we see today is that in order to meet the net zero emission goals, there are great attempts, for example, to go from gray hydrogen to blue hydrogen. In the case of conventional hydrogen production methods, like steam reforming, carbon capture, utilization, and storage, CCUS, is being used in order to retrofit or revamping projects or existing plants. Some advanced catalysts are being used for post-combustion CCUS. However, due to the cost increase compared to the original technology, we actually do not expect much focus on the development of greenfield projects of SMR with CCUS. However, we do see increasing projects for revamping and also for retrofitting CCUS in existing facilities. There is a different case for partial oxidation, since the partial oxidation is a highly exothermic reaction and the reaction energy can be used for steam production. Then the higher operating cost due to higher pressure, and also the cost from CCUS can be partially offset with the steam production. And therefore here we do expect some greenfield CCUS for partial oxidation and also retrofitting. In the next case of orothermal reforming, there are no current pilot projects on this that are operational, but there are very interesting projects, like, for example, in North England, the H21 project, which is aimed for the construction of a plant with a capacity of 12.15 megawatts hydrogen using orothermal reforming. So next slide, please. Isidro, could you please change? Thank you. So now, in the case of green hydrogen, in the last year, there has been a very strong development in electrolysis. Actually, electrolysis is a very old technology. Alkaline electrolyzers have been used for more than 100 years in the ammonia production. What we see right now is that there is a higher attempt to increase the efficiency of the electrolyzers, also to increase the scaling up of the electrolyzers, and also to include different materials. In the 1950s, the polymer membranes were developed, and therefore the pens were introduced into the market. And now we see a higher focus also in solid oxide electrolysis due to the development of advanced ceramics and perovskites. So what is the future here? The future is to reduce cost, OPEX and CAPEX cost by improving the conditions, the operational conditions, increasing them, improving efficiency, but also introducing new materials and increasing the lifetime. So we can see that there is also some new trend for new technology development, like, for example, membraneless electrolyzers or microbial electrolyzers. Also, we see an attempt to reduce the operational cost by making the stacks less sensitive to the water in order to reduce the cost from water treatment. And there are also some developments for electrolyzers operating, for example, with salt water. Next slide, please. As I mentioned before, alkaline electrolyzers are like a mature technique, and the stacks are getting bigger and bigger. From the insurance perspective, we say that they have a proven technology up to 4 megawatt per stack. It does not mean that these are the biggest megawatts stacks that we see, because more or less since the 2020s, we see almost every couple of months the news that the world record has been cracked and a bigger alkaline electrolyzer has been installed, 10 megawatt, 20 megawatt, even 30 megawatts, like the example that we have here of this company in China, where a 150 megawatt capacity plant started commercial operation in November 2021, and it's aimed to generate electricity from wind energy for the electrolyzers, 200 megawatt. The thing with alkaline electrolyzers is that the membranes used, they are permeable for hydrogen, but also for oxygen, meaning that during load changes, there is a fluctuation of hydrogen and oxygen between both electrodes, and therefore there is an inherent higher risk for explosion or for a process runoff. This means that some limits must be included in the process safety, and the limit varies between 2% hydrogen concentration to 4% hydrogen concentration in oxygen. And also the diaphragm durability can be limited during operational regime. Next slide, please. We see nowadays a really great interest in the further development of the polymer electrolyte membrane electrolyzers, which works with the proton exchange membrane technology. We see here important advantages, like, for example, it has a higher pressure operation, a fast response, dynamic operation. However, it works under high acidity and corrosion conditions, and therefore pretty expensive catalysts like iridium or platinum are required for the electrodes, which of course increases the capex costs. The membrane that is used, this polymer membrane that is used, has the advantage that is only permeable for hydrogen, meaning that the load changes do not affect or do not tend to a process runoff, meaning that this process is inherent safe, well, with respect to explosion from the reaction point of view. However, there are also problems regarding the aging of the components, and upscaling of the PEMs is not that easy due to the rare components materials being used and the cost. Next slide, please. Isidro, next slide, please. Okay, so the last technology that we want to show you in regard to electrolysis is the solid oxide electrolysis. It works at very high operational temperatures of 500 to 600 degrees, meaning that the efficiency is can be higher for this kind of electrolyzers, and has the advantage that it can also be used as a solid oxide fuel cell, meaning it can be used for hydrogen, whether for hydrogen production, also for electricity production. It uses advanced ceramic materials like yttrium stabilized zirconia, and for the electrodes, also advanced perovskites. So far, there are only pilot projects, therefore is only limited experience, but it's a very promising technology. There are important pilot projects, like, for example, the Green Industrial Hydrogen project, which works with reversible high temperature electrolysis. It's a project from Sunfire and has a capacity of 150 kilowatts. In our inside document, we give extensive description of the different production methods for hydrogen, also the advantages, the disadvantages, and also the risks. So if you are interested, you're very welcome to take a look into our document. And now Isidro is going to talk about the industrial applications.
Thank you very much, Isabel. Good afternoon to everybody. My name is Isidro Pimentel. I work as an underwriter at Zurich in Germany. Hydrogen is used as a feedstock or fuel in several industries, including petrochemicals, food industry, and pharmaceuticals, as well as metals manufacturing. For decades, hydrogen has been used as a raw material by the chemical industry, mostly in the production of ammonia and hence fertilizers, and in refineries where hydrogen is used for the processing of intermediate products. In metalworking, hydrogen is used in alloying and iron flash making, among other uses. Especially attractive is hydrogen as energy storage medium. As a matter of fact, the International Energy Agency recognized that hydrogen is one of the leading options for storing energy from renewables. As you might know, one of the main challenges of renewable energy is the seasonal fluctuation, which represents a big challenge for the distribution networks of the future. Hydrogen looks in this sense as very promising to be a lowest cost clean option for storing electricity in the years to come. While renewable electricity can help reduce emissions in road transport, in the areas of low temperature industrial processes and heating, fossil fuels have today a significant advantage in applications that require a higher energy density. Industrial processes that rely on carbon as a reactant, or where demand is seasonal. In these hard to abate sectors of the economy, and especially hydrogen, and especially green hydrogen, could become a game changer for the decarbonization across many industries, and its utilization, in our opinion, is going to vary from small, decentralized solutions to world-scale projects with high complexity. The use of low-carbon hydrogen in refining and ammonia production faces an economic barrier today due to the higher cost. However, replacing the production capacities with low-carbon technologies, as my colleague mentioned before, will not be as technically challenging as adopting hydrogen for new applications. Policy making for a green future needs to address not only the production side, but also the demand. In fact, this is like the old question about the chicken and the egg. Industrial applications are today an ideal opportunity to ramp up low carbon hydrogen demand while decreasing the CO2 emissions from processes. And we have some examples. Projections depending on policy making estimate that around 190 million metric tons of hydrogen could be used by 2050 in a scenario where global warming is limited to 1.5 degrees. If a strong policy is enforced, 700 million tons of hydrogen could be used. This will require around $11 trillion of investment in production, storage, and transport infrastructure. If all the unlikely to electrify and hard to abate sectors in the economy will use hydrogen, the demand could rise as high as 1,400 million metric tons by 2050. Of course, these are projections which are influenced by technological development, cost reduction, and policy making. All this leads to the question, where is the green energy for hydrogen production on such a scale coming from? While the paper doesn't focus in detail on policy making, we expect that A, different sources of hydrogen will be needed during the transformation process, even fossil-based, such as natural gas or nuclear, and B, this fact will in turn influence political decisions, infrastructural investments, and ultimately will have an influence. Unveiled in January 2022, plans to label some gas and nuclear power as green, stating that it is necessary to recognize that the fossil gas and nuclear energy sectors can contribute to the decarbonization of the economy. Meaningful volumes. This is why it has been discussed establishing technology-specific policy support for green hydrogen in the form of a green hydrogen quota. The paper includes a table summarizing global policy making. Such a quota will create a stable demand for green hydrogen and ensure the financing of the technology learning cost. An example for the decarbonization of the heavy industry is steel production. As shown in this picture, green hydrogen can be also used to displace the use of an ancient industrial apparatus that is the blast furnace for iron production. Side shows that iron ore concentrate is pelletized using fossil fuels. Pellets and coke are today fed into a blast furnace, which produces hot metal, which is then transformed into crude steel. As an alternative, on the right hand, there is a hydrogen route in which iron ore concentrate is also used to produce pellets, but no fossil fuel is used for that. Hydrogen is used for two purposes in this process. One is the production of high-grade industrial heat for the process, and the other one is for the direct reduction of iron ore into metallic iron, which gives origin to sponge iron, without using coke as a reducing agent, without using fossil fuels for heating, emissions-free. The sponge iron is then used for crude steel production. As a matter of fact, most iron producers today announce to decarbonize their production using this method. For example, ThyssenKrupp in Germany. With this, 90% of the emissions compared to the current processes. This means for ThyssenKrupp alone, around 6 million tons CO2 per year savings. Gas turbines and other engines can be adapted to burn hydrogen, and the scaling up of fuel cell plants is ongoing. Most of the gas turbines projects nowadays are sold as H2 ready in different configurations. But for most manufacturers, using the current combustor, it's not going to be from 0 hydrogen to 100% hydrogen. The discussion in many places is about incremental shifts and case-by-case solutions. The picture here illustrates, thank you very much, and apologies for that. Again, the picture here shows the differences between different fuels. On the top, you see a hydrogen flame, pure hydrogen. In the middle, you see a combination of 50% hydrogen and 50% CO, which is a simulation of syngas. And on the very bottom, you see a simulation of natural gas, which is methane. The combustion characteristics of hydrogen differ from natural gas very much, and this is a challenge for the design of hot gas path components, especially the gas turbines, combustors. The reasons are the high reactivity of hydrogen and a lower density. Hydrogen combustion leads to instabilities known as thermodiffusive combustion stabilities. The picture on the top shows damage due to high frequency thermoacoustic instabilities after inappropriate tuning of the machine. The higher flame speed of hydrogen increases the risk of flame propagation upstream, closer to the injection points. Flames, again, hydrogen on the top and natural gas on the bottom, and you see the flame reactivity, which is the main challenge for today's combustors. And on the right side, on the top, you see some damage due to these thermoacoustic instabilities. And on the bottom side, on the right, you see some flashback damage to fuel nozzles. That means new types of combustors will be needed to be developed to be able to burn 100% hydrogen without the need for diluents for emissions control. And to our knowledge, this is in development by most of the major manufacturers. We held interviews with some of the research and development departments of major manufacturers and described in detail in the paper their approaches and challenges. The development of retrofit solutions for existing gas turbines will be key for the implementation of the hydrogen gas turbine technology. The periphery components and material selection needs special attention due to, for example, embrittlement and operational safety. At this point, I would like to pass to my colleague Louis Terry to talk about storage and transport.
Hi everyone, I'm Dr. Louis Terry. I'm a research scientist at the Bristol Composites Institute, and it's my pleasure to speak to you about the final arm of the hydrogen economy, storage and distribution of hydrogen. Okay, we've got some slides. The idea of the hydrogen economy is not new, and it's been pushed for decades but failed to gain momentum until now. One of the main factors for its recent impetus and global adoption by governments is due to recognition and acceptance that hydrogen is a viable option to cleanly store energy from renewable sources securely and over long periods of time, giving countries and governments ways to secure greater fuel autonomy and allowing them to decarbonize as well. In this IMEA Insights paper we're releasing, we give an overview of some of the storage mediums and methods proposed and for you to be aware of, as well as their individual risks and potential future technological landscape that lies ahead. Now, compressed gas storage is the most technologically mature storage method that you may well know, with many types of storage cylinder available, and new designs coming up on the horizon, potentially eliminating the explosion risks associated with compressed gas. The liquid storage method is also a very technologically mature method, with all major industrial gas suppliers using liquid delivery tankers of hydrogen. As a liquid, this is great because you increase the amount of product you can store in the same volume, but you've got cryogenic refrigeration equipment needed, and this comes with increased footprint costs and risks. Sorbent materials you can think of as molecular sponges, reducing the risk of high pressure. We use low pressures here to suck up the hydrogen. These are not as technologically mature and still require some work, and will likely be seen first moving into transportation market. Chemical hydrogen storage, you may well have come across or heard of metal hydrides. This is where the hydrogen is chemically bonded to metals, and within this, thermal management of this storage system is key. There's also liquid organic hydrogen carriers we discuss, including ammonia, as well as some alkanes, whereby various catalytic methods are able to release the hydrogen from the carrier. And finally, we also discuss some of the salt and rock cavern storage that is being seen across the globe, such as the Advanced Clean Energy Storage Project in Salt Lake City, where there will be, or there's expected 150 gigawatts of storage capacity by 2025. But no matter which storage medium we're talking about here, the same risks are related to all of them, and they always link back to leakage, rupture and failure to detect. This may be through containment material corrosion, hydrogen embrittlement, which Isidro touched on, valve conditioning, pressure relief devices and purge and release mechanisms. But of course, there's also, if we're storing the hydrogen, we also need to transport the hydrogen and distribute it. And the major bit of infrastructure here that we'll be seeing is pipelines. This will be either refurbishment of natural gas pipelines or the implementation and building of new hydrogen pipelines. There's discussion between 100% service and also natural gas hydrogen blends. in the European Hydrogen Backbone Initiative, there is around, I believe, 116,000 kilometers of new pipeline expected to be built, and around 40,000 kilometers of repurposed pipeline just in this project over the next coming decades. But the same thing again relates to this, is leakage, rupture, and failure to detect, with some similar failure mechanisms we may well be aware of from other pipelines, including gasket failure, poor welding and valve condition, but some more new ones, including hydrogen embrittlement and containment material corrosion. All of this will mean that there will need to be an increased maintenance and support of pipelines. And there are actually some historical claims out there relating to leakage and explosions, such as the Specialty Silicones plant explosion, where failure to detect a leakage in their pipeline caused an explosion. And this is discussed in the paper. Now, finally, obviously, one of the new things you may all be wondering about regarding hydrogen is hydrogen embrittlement. And what I would like to stress here to all of you is that currently there is no structural metal that can be labelled as immune to hydrogen embrittlement. Each metal has a varying degree of susceptibility, and there's not a magic list that we can just pick from to say that these are invulnerable. However, we can avoid susceptible metals and alloys in our pipelines, in our containment materials, etc. And there's a lot of work and research on this. It's a question of when, not if, so time. And likewise, regarding hydrogen embrittlement, when we're talking about elastomers and plastics, these are known to be less susceptible but permeable to hydrogen, so there may be some loss in high pressure pipelines or high pressure storage. You can find more details of this obviously in our paper and the upcoming IMEA paper as well in September. I'll finish here and pass on to Carl, who's going to speak to you about the underwriting.
Thanks, Louis. Thank you. Yes, Louis mentioned hydrogen technology as such is surprisingly old, but it is being used in a new way. And that, of course, creates new risks. So while obvious risks that we know of, such as, for instance, fire and explosion, continue to remain an issue, we also need to think about these new risks and less obvious risks. And we are listing a couple here. There are more in the paper, so please take a look at this, but I'm taking you through these here. Well, first and foremost, design and defects. We mentioned the lack of standards. This means there will be a lot of prototype equipment, unproven equipment, and people need to be aware of defect exclusions, maintenance covers, and also warranty covers. Hydrogen comes in modular forms. Electrolyzers come in stacks. They are being scaled up. So this means repetitive operations, the same kind of equipment being used over and over again, and this calls for serious loss clauses. Also, people should think about the occurrence language in policies and the event definition. So how many losses, for instance, constitute one occurrence, and so on and so forth. Testing and operation is very critical. As we've heard, a lot of the risks with electrolyzers comes from the altering patterns of operation. And again, here, there's little standards, there's little experience, so proper policy terms, solid definitions, and also deductibles should be considered. Storage and distribution remains a key risk, as Louis just mentioned. It involves a lot of existing assets, and of course, the question is are these assets, is this equipment fit for purpose? Is there refurbishment needed? If so, according to what standards? So people really should think about this when they reflect on replacement value, when they reflect on the scope of indemnity. What about secondhand? What about pre-used equipment in projects? Downstream integration is another topic. There are risks to or resulting from existing property. There are third-party liability risks. There are integration risks with existing processes. Think, for instance, refineries, hot tie-ins, and so on. So again, here people should think about deductibles, about defects cover for downstream equipment. Also, for instance, when we talk about gas turbines. And one last thing in that regard are external MPL scenarios. So your electrolyzer plant, if it sits next to a refinery, may well be subject to 100% MPL that simply results from a vapor cloud explosion at that refinery. So keep that in mind. It's highly integrated. It's a complex value chain. And the last point, DSU and BI risks. Of course, there are increased interdependencies resulting from this new business model that we are seeing between electricity production, hydrogen production, and hydrogen off-taking. And this needs to be closely considered. Also, with the fact, and we're going to touch upon this, that some of the equipment that is used in hydrogen projects, especially on world-scale projects, has quite lengthy lead times. Now, with these considerations in mind, I would like to hand over to Isidro for the risk mapping that we've conducted.
Thanks. You might allow I let the camera switch off. Don't touch the working system. Looks like it's working right now. Apologies for that. During the work within the group, we will risk mapping regarding risks associated with hydrogen. We draw some conclusions. For example, risks associated to design, especially to material selection and operating parameters, such as embrittlement, corrosion, erosion, can be considered as risk clusters relevant to all hydrogen applications. Same applies to the main exposure, which is explosion, which increases sensibly the relevance of high design standards, detection systems, leakage control, and especially operational excellence. This is even more challenging while retrofitting existing plants and processes. High exposure and rather severe worst case scenarios derived from feedstocks. Same applies for the human factor, negligence, malicious damage, lack of experience, lack of training, lack of procedures, especially emergency procedures, as well as cyber exposure, can rapidly aggregate to catastrophic events. That means access control, work and safety procedures, safety plans, emergency plans, and cyber security are more important. A number of applications are being investigated and developed, implemented, and scaled up. Every second day you hear about new project about hydrogen, a new application, and new technology. That means the prototype nature of most applications will, in our expectation, remain for many years. Again, it is important to point out that not only prototypes and unproven technologies are critical. The scaling up of components, for example, you can parallelize the number of stacks, but then you will have challenges while designing the compression system, the storage, etc., balance of plants. The design and operational procedures, as well as standards addressing the human factor, represent, in our eyes, the key risk element to consider. From the perspective of an insurer, this aggregative nature should be considered not only in regard and while performing risk engineering assessments. The insurance industry will face some non-assessable risk in the years to come. Some others should be carefully and actively addressed to ensure manageable and fair risk transfer in a hydrogen-based economy with many disrupting players, sometimes with low experience in the process integration. Some weeks ago, I personally had a discussion with a client planning a huge project in hydrogen production. And they were engaged already with known equipment manufacturers providing the technology. But the process integration, the assessment of hazardous operations, the defining of procedures, is relying on the client's team of a couple of engineers. I think personally, any doubt, a better platform and a wider experience managing projects of this size. No doubt, underwriters will rely heavily on engineering for knowledge, for direction, to profitably underwrite a potentially difficult class of business. At this point, I would like to pass to my colleague, Jan Rogener.
Hello, a warm welcome for me. I'm Jan Rögener from AXA GI Germany, working in risk and claims. I still see the risk mapping page, but I can start talking. Next page, please. So what happens if the risks materialize? We've researched claims databases on historical claims related to hydrogen in general infrastructure, including storage, transport, and chemical industry, refineries. And you can look at the root causes on the left, or better read the paper for more details. There are two statistics on the right top from the HIAT 2.0 databases. But these statistics do not represent the future expectations, especially not on new technologies like large electrolyzers and renewable energies. Just shows that hydrogen has been used in different applications in the past already. Can you click on the bottom? There should appear a real claim example. So in the real claim example, green hydrogen production, some risks materialized. An experimental fuel cell power system exploded in the South Korean city of Gangneung during a test operation. 3 tanks of 40 cubic meters capacity, each were all destroyed and sent debris across an area of well over 3,000 square meters. There's no additional slide, it's just some text. Yes, thank you. How did it happen? A static spark started the explosion when oxygen concentration exceeded 6% in one of the buffer tanks. If you took notes from the previous slides, is above the allowed limit. The oxygen removing component appeared to have been omitted during system implementation because it was not available before project completion. The static spark remover in the buffer tank was also omitted during construction because of difficulties to implement. The system had an asbestos separation membrane that had to be operated at a minimum of 98 kilowatt hours. Due to the solar power energy source, the system often operated at a level below the necessary 98 kilowatt hours, leading to membrane degradation. The oxygen concentration detected to be higher than 3% was ignored to reach the 1,000 hours required for experiment validation time. Finally, the safety management team did not follow safety regulations that required it to monitor hydrogen quality daily. So many risks materialize. So how would the policy respond in these circumstances depends on the combination of what obligations are placed on an operator by underwriters to review installation procedures, and also what requirements are on the insured to conduct adequate maintenance and rectification. New technology part is the membrane. The consequential loss to the unrelated components are hard to reject via a lag, for example, lag 1 clause on the membrane. So failures might be caused by the combination of new technology, new operator, new contractors, and a new scope of work, or say it shortly, a lack of experience. Please read the paper for more details. Thank to all contributors, especially to Isidro. And now I'd like to hand over to Franco.
Hello, everybody. I am Franco D'Andrea, a legal director at Clyde & Co. In the full paper, we are going to look into our crystal ball, and we're going to consider a number of hypothetical claim scenarios and issues. What is on this slide is simply a snapshot of some of those issues that are considered in more detail. Now, one feature of electrolyzer membranes that we've been hearing is that they require a consistent power supply. With that in mind, if we picture a hypothetical green hydrogen project, say a hydrogen production facility that's connected to a wind farm, What happens when the wind input is reduced or when the wind input stops over any given period? Now, accordingly, underwriters, in our view, are well within their rights to ask about what alternative power supplies are available to maintain that consistent power supply that's required. Now, it's also likely that claims professionals, when they come to consider these claims in relation to membranes, will need to be asking these same questions at the claim stage. But there are two related issues to this point. Firstly, the fact that an electrolyser is a very significant proportion of the overall costs of an industrial hydrogen project will clearly mean that any claim in this area has a potential to be significant. And secondly, the lifespan of membranes and diaphragms, as we've been hearing, are limited and will be heavily dependent on the consistency of the power, but also on the project's operational regime. Now, the consistency of operation within design parameters is then clearly something that claims professionals will have to consider when faced with hydrogen claims of this type. The same can very much be said about hydrogen infrastructure becoming obsolete quickly. We heard earlier from Isabel that electrolysis development has moved towards PEM or PEM electrolysis, but even now, new membranes are on the horizon. So from a claims perspective, what happens when a customer's entire electrolysis concept becomes obsolete around the time of a claim? That's another challenge that claims professionals will be facing in the years to come. Another issue is the replacement components and the materials that make up those components being very expensive and having very long lead times. Now, we appreciate, of course, that this issue does not only affect hydrogen infrastructure now, but new use technology is almost always likely to face the greatest risk in demand. By way of example, it isn't just the membrane or diaphragms that are tailor-made to a project. The same can be said of, say, hydrogen compressors, and lead times for those items, as we understand it, are at around 18 months at present. Now, that is, of course, a significant issue for your physical damage type claim, but any lead time like that is also very significant for business interruption. The final taster I wanted to mention now, that's considered in more detail in the paper, is whether underwriters are now ready to consider risk allocation with their customers in the event of supplier insolvency and how that plays out in any given claim scenario. Now, I make no apology for repeating again that we're dealing with here new and cutting edge technology, but with that new technology comes opportunities as well as risks. But from a risk perspective, what happens if the supplier of your, say, bespoke electrolyser membrane system becomes insolvent? In other books of business in recent times, underwriters have faced claims that should probably otherwise have been recoverable from a manufacturer under a warranty, but the relevant manufacturer has then gone into insolvency. How this issue is then approached by the insurance market, by different insurance markets, and by insurers communally will be a significant feature, in fact, one of the defining features of the early years of insuring green hydrogen projects. I'm now going to pass you back to my colleague Isidro for a final wrap up. Thank you.
Isidro, is that up to you for the final closing?
Yes, Mattia, you can add whatever you want. Just want to mention we are thankful to the audience for joining us today. We were, of course, unable to discuss all topics in detail today during the webinar. We wanted to raise the interest for the publication. At this point, we will be able to answer your questions. Before that, I would like personally to express my gratitude to the EMEA Executive Committee for giving us this opportunity, and especially to all contributors, all of them providing valuable insights from different perspectives. Thank you. Thank you very much for a great teamwork. The link to the paper is shown below and in the chat. You can download it for free at the EMEA website. The working group paper will be presented at the EMEA conference taking place from 18th to 21st of September in Dublin, Ireland.
Perfect.
Would you like me to read out the questions?
Oh, yes.
Over to you, Mattia.
Stephanie, as you want to know, I wanted to personally thank all the contributors to the paper and to the presentation today. And yes, of course, we have a couple of questions which we have received in the chat. So please, Stephanie, go ahead. So the person who is the best in the speaking panel can pick them up and answer. Then we will see if there is any question from the audience. Thank you, Stephanie.
Okay, we've got two questions that came in right at the beginning. One is, how do you define proven, and is proven a question of capacity or a variety of factors such as capacity, pressure, current, materials, etc.?
So thank you, Stefan. I think this question is addressed to me. We do not have any definition of proven. What we've seen is the typical bathtub curve. When you have a new development in the early years, you have to deal with all of the problems due to faulty design or design issues, process safety, materials, and so on. As I mentioned, the technology itself is not new. The problem is the scaling up. And of course, scaling up brings some problems with it, because the bigger the stacks are getting, then of course the behavior of the process is different. What we want to see is field experience with all what it requires, meaning load changing, real operating conditions, high load, base load, also the condition when the stacks need to be energized, but no hydrogen is being produced. And we are actually discussing with our colleagues that what we want to see is at least 8,000 equivalent operation hours. We are seeing that this terminology EOH is also being applied, which is common for gas turbines, is now also being applied for electrolyzers, since the downtime when the stacks are energized, it also affects the lifetime of the components. And we want to see that when a new product is introduced to the market, that these early issues are being addressed and solved. That's why we do not talk about proven technology when one new electrolyzer starts the first year commercial operation. I hope that I could answer your question.
Maybe
Thank
from
you. And
Stephanie, maybe just a quick feedback from my side in that regard. I think we have to differentiate, and I agree to all points raised by Isabel. Have to differentiate on the other side between prototypes and new applications. For example, we learned that a hydrogen compressor, an industrial hydrogen compressor, is always a tailor-made product. So we don't expect that the very same compressor, which is planned for the project, has to be tested with 8,000 hours and monitor. We know similar compressors in the technology, in the components, in the materials have been tested over the years. So we need to differentiate. But as my colleague said, it's a lot of different factors, and we will see a lot of new technologies emerging. We will see replacement of materials because some of the rare metals are really a cost factor. So it's a combination, to answer the question, it's a combination of many factors.
okay, can I go ahead? The next question is from Matthew Thins. For upcoming projects, what is the typical planned capacity per alkaline electrolyzer stack?
Well, I think this is also a question for me. We are seeing a very fast development on this regard. I think the first single stacks with a capacity of 1,200 normal cubic meters per hour, start commercial or are starting commercial operation right now. So I think we should expect single stacks of 10 megawatt up to 30 megawatt in the upcoming years. I think this is going to be a very fast development because it's also some raise that in order to achieve, because the bigger the electrolyzers are, then also the lowest the cost, the OPEX, the operational cost, and therefore in order to make them more financial competitive, then bigger electrolyzers are being aimed right now, and also in order to increase the efficiency.
Okay, there's no more questions. If there's anyone who wants to type in a question or raise their hands, I will try and zoom in and allow you to speak. So raise your hands if you want to ask a question. Okay, so no more questions. If you have questions that you think about later, just send an email. Over to you, Mattia, to just finalize.
Thank you, Stephanie. Yes, of course, as it has been said by presenters, this is an insight paper, which you can see the link, and I also posted it in the chat, and it's already available on our website. Anyway, all the documents and discussions and all the things that you have seen now have been produced as a part of a working group paper, which will be published after the conference in September, and an extensive presentation on the findings will be also held in Dublin during the EMEA conference 2022. So the usual paper will be available later on, but for the time being, you will have this deep insight one, which is very extensive with a lot of technical details, and all the information will be then condensated in a more usual format like EMEA papers have been done so far. For the time being, I can also only say a huge thank you very much to all the contributors which took part in the working group paper, and of course to Stephanie for the support for this webinar, and to all of you who have joined today listening to our presentation, which I hope is going to be helpful for your new business. And of course, you can find more information in the paper at the link below. So thank you, everybody. And I would also like to give you all greetings from all the presenters, and have a nice rest of the day. Thank you.
Thank you. Bye-bye.
Thank you very much.